So, welcome to this week's CPPC seminar, and today's speaker is Giovanni Pierobon, who requires no introduction, I believe. But anyways, just in case you want to know, he's postdocing for me at the moment, and he was previously a student, PhD student, graduated in, when was it, 2023, I believe. Yeah. So anyway, so he's our local simulation expert. And so he's going to tell us about axion dark matter and simulations thereof and implications for direct detection. So thanks.
Yeah, thank you for the introduction and everyone for connecting. So indeed, I'll be talking about some of the work that I started doing during my PhD and is sort of continuing to this day on numerical simulations of axion dark matter in particular, and what can they tell us for direct detection experiments that have been built to detect these particles. Before I get started, I want to say just feel free to jump in and interrupt me if there's any question or anything is unclear. And I don't mind if we have a bit of discussion along with the talk. All right, so let's get into it. First of all, I want to spend some time with the motivations and try to talk about why do we even bother talking about QCD axions and their role as dark matter candidates, and how do experiments are actually already trying to discover them, excluding part of the parameter space and proposing new ideas to detect them. Having said that, the focus of the talk is essentially in part two, where I'll be discussing the role of the simulations starting from the early universe, where we have this network of the topological defects, down to the small-scale structure formation, which is sort of similar to what we usually see in standard cosmology, but it will be taking place at very much smaller scales. So it will be in particular subgalactic scales. And finally, I will wrap up discussing on how all these simulations can tell us, and more importantly, can tell the experimentalists on how to look for the axions in the near future. All right, so it's not a QCD axion talk without a strong CP problem. I'm sure that most of the audience is familiar with the strong CP problem and the axion, but if you're not familiar, don't worry about it because I'm not going into all the technical details. I will just try to summarize the big picture here and then just to try to get everyone on the same page. So as the name suggests, strong CP problem is related to the strong interactions and the CP symmetry. Now, the CP symmetry, the discrete symmetries, charge and parity transformations, and we know that this combination of C and P is not a good symmetry of nature. We know already from the weak interactions that this is not a good symmetry of nature. So these are some questions for us to ask if this happened also in the strong interactions. So we look at the theory. Our best shot in quantum field theory is QCD. We build QCD and we have a CP violating term in the Lagrangian, which is this theta and GG duo. Now, G is just a gluon field strength, so you can think of this interaction of this theta, which is an angular parameters with the gluon field. And these parameters, as I said, can be thought of as an angular parameter and could take any value from 0 to 2 pi. Now, what's important about this is that because of this interaction, we have a clear prediction as well on an observable, in this case, an electric dipole moment for the neutron. That will be in principle proportional to this theta bar parameter. So if we look at the calculation, it will be something like 10 to the minus 16 times this whatever value of theta bar in units of electric charge centimeter. So we have a clear prediction. We look at the experiments. Indeed, as you can see in this plot, as a function of time, the experiments have gotten better and better at measuring this quantity. And so far, we have no evidence for a detection of this quantity. And if you see, for example, the last point here is a measurement of just five years ago. We have a very strong bound on this EDM to be around 10 to the minus 26 e times centimeter, which poses a bound on theta bar to be smaller than 10 to the minus 10. So this is very puzzling. This is odd because in principle, as I was mentioning before, theta bar should be a fundamental parameter of the theory of the standard model, and could take any value from 0 to 2 pi, and there's no actual reason for us to imagine that this value would take such a small value. The idea that Peccei and Quinn had almost 50 years ago now was, well, maybe there's a dynamical explanation to this puzzle, and they thought of, well, what if we extend this parameter to be a degree of freedom, so the dynamical field, in this case, A of x is a field. We normalize it by an energy scale. So Fa is called the axion decay constant, but so that A over F sort of acts like an angular parameter. And if you have the similar coupling to the gluons, then this is actually you can show that you can write this as an effective potential, which under a certain approximation has a very simple form, this one minus cosine of the angle. And now just by minimization, the field will want to find a configuration of minimum energy. So we'll definitely roll down to the bottom of the potential around 0, where it was shown also some time ago by Buff and Witten that at t equals 0, you have a CP conserving value. So we have an agreement at that point at t equals 0 with the experiments, so that the value of the field is as close to 0, at least to 1 part in 10 to the 10. So this is in a nutshell the solution to the strong CP problem, and we have the axion as a real scalar field, but when we embed it into a UV complete theory, so a theory that has to be consistent in all energy scales, this axion field is actually an angular degree of freedom within a complex scalar field. So in order to have for the axion to have all the properties that we want, we need a spontaneous symmetry breaking mechanism. This is like in the Higgs mechanism. You imagine you have this Mexican head-like potential where you initially have a U1 global symmetry that is broken at scale FA. So FA acts as a control parameter in this case. And then the axion is born as the angular degree of freedom, and it's basically highlighting the residual symmetry that you had before the breaking. So I want to highlight 2 things. First of all, it is a known fact that if you have a spontaneous breaking of a U1 symmetry, you eventually end up with topological defects, in this case, cosmic strings. So I want to point out straight away that strings arise at the scale FA because of this breaking. And I will discuss the strings in the second part more in detail, if you're not familiar with them. And the second thing I want to emphasize is that if you look at the actual potential in the radial direction, it's actually flat. So there's no preferred direction for the axion to take place. At the spontaneous breaking of the symmetry, we'll take a random value within this circle, but there's no preferred value. So this is relevant because at a much lower energy scale, you imagine after the universe expands and the temperature cools down to the QCD scale. Now the QCD interaction are switched on essentially. So you have this potential 1 minus cosine that I was showing before that is gradually becoming more and more relevant. So if you look on the right-hand side already, you can see that the flat direction starts to shape itself into a potential that has a bottom well at t equals 0 and any multiples of 2 pi, since the potential is periodic. And the other thing I want to say here is that because of this explicit breaking, we have the formation of another type of topological defects, which are the domain walls. So domain walls only form at the QCD scale, while the cosmic strings will form at a much higher energy scale. Now, if we have a potential, we also have a mass. As you can imagine, oscillation around the minimum of the potential are to a good approximation harmonic. And we know that a second derivative of our potential is a mass. So from theory and from our potential developed by the theory, we have a prediction also for the mass. And that this mass is essentially established by standard model parameters like the up and down port mass, the pion mass, and the pion decay constant. And that is essentially fixed by whatever value of FA we take. So the mass is inversely proportional to this FA. So the higher your FA symmetry breaking scale, the smaller your mass. So I'm also quoting some numbers here. So for a typical value that is not excluded, so this is a fairly large number in energy scale, we have ballpark microelectron volt mass for the axion, which is much smaller than any other standard model particle. So here I want to highlight that QCD axion is a one parameter model. Once you fix the scale FA, you fix the mass, and then you fix any coupling, whether to photons, to regular matter, any other particle you want to come up with. All these interactions are suppressed by this 1/f factor. So if you look at the typical parameter space plot, I will show many of these type of plot in this talk. You can see that in the vertical axis you have the interaction strength, and in the horizontal axis you have the value of the axion mass. Since these parameters are degenerate by FA, you would want the axion to lie in a straight line, essentially. So in here, the yellow band is actually taking into account that you might have some order one different parameters based on the UV completion, and the standard benchmark that experiments are using are these KSVZ and DFSZ, which are UV completed models that have been developed right after the Peccei-Quinn mechanism. So we want to lie in essentially in this in a line in the parameter space in order to solve the strong CP problem. The other thing I didn't mention is why the value of the FA has to be that large. Well, that's because since the coupling of the axion is suppressed by 1 over FA, if FA is small enough, then the coupling is large enough for an experiment to have detected or the axion, whether it is in the lab or through astrophysical environments, any sort of constraint. So at the moment, up to some order 1 differences, the value of FA has to be larger than, let's say, 10 to the 9 GeV, which is far beyond the scale of colliders. Yeah, so yeah, we discussed the axion and how can there be dark matter, and it turns out there's a very simple mechanism to get dark matter, and I will discuss that in this slide. But first of all, I want to discuss the 2 scenarios that we have in cosmology, because I talked about spontaneous symmetry breaking, but we have to relate that to the inflationary scale, because if the symmetry breaking happens before or after inflation, you have a completely different phenomenology. So the first case is the pre-inflationary scenario. So imagine that FA is larger than any Hubble scale of inflation. So the symmetry breaking happens before the end of this inflationary period. And at symmetry breaking, the axion field will take a random value from 0 to 2 pi, anything really. But then because inflation happens after, whatever value you chosen in any of the causal patches will be stretched to super horizon scales, and which means that our observable universe today, because of this stretching of inflation, will be contained in one of these patches, and there's no reason for us to know what was the value of the axion field initially at the time of symmetry breaking. But the system is very simple, because you have a differential equation for the axion field that looks a lot like a damped harmonic oscillator. At initial times, the Hubble drag term wins over the potential because the potential is basically negligible and your field is stuck at the initial value. But then as the potential and the Hubble term become comparable, you start to see this oscillation around the bottom of the potential. So this is called the misalignment mechanism, because you initially start from a value away from 0 and you roll down to 0 because of the potential. And if you look at the equation of state in these oscillations, you can see, if you look at the energy density, for example, you can see that it scales with the scale factor to the power -3. So this R, capital I, is a scale factor. I use A already for the axion field. And this scaling is essentially no relativistic matter. So, a scalar field which is oscillating around a quadratic potential behaves as a dark matter candidate, essentially. So this is very neat. But we still have, the problem that we don't know where we start our oscillations, because if you start at a larger initial value, you end up with more energy produced. So this omega A is the relic density today of axions that depends on the mass itself, or FA. But in principle depends on a random value. So our theory here has no predictive power, because there's no way for us to say what is the value of this angle. Nevertheless, if we fix this to be order 1 or 1, we end up we can match the relic abundance of axions with the observed dark matter abundance and figure out what is the value of the mass to give us exactly that equality, and that is around 10 microelectron volts. So this is why typical telescopes will look for axion at those values of the mass. Now, the second scenario, which is what we'll be focusing on, is the post-inflation scenario. Now, here the opposite happens. Symmetry breaking happens after the end of inflation, so there's no stretching of these causal patches, and our observable universe is made of a lot of these patches that were causally disconnected at the time of symmetry breaking. So the system is much more complicated, because now we have these different patches getting into causal contact with each other and interacting. So the equation cannot neglect the gradients in theta or in the axion field. But if you look at the misalignment mechanism, this is entirely predictable, because now we have the exact same mechanism. All different values will start at different initial angles, but then they all converge at 0. And even if you don't know all of the initial values, you can take a stochastic average, and figure out what is the value of the Rayleigh density. So in this case, we could essentially single out a very precise value of the mass. However, we have a different second contribution to the Rayleigh density that comes from the decay of strings. So the emission of axion from strings. And the strings arise, as I was saying before, because of the U1 symmetry breaking. And in here, for example, you're seeing a slice of the axion field, A over F, between minus pi and pi. And you can see that the value can take any value from minus pi to pi continuously in certain regions, and that's around one of these strings. So the system is much more complicated. It cannot be solved analytically, and we need to rely on numerical simulations for this. And that's essentially our introduction to why we need simulations. So I want to, before I discuss how heloscopes are trying to find axions, I want to provide a bit of context on where in the parameter space we're looking at. So this is a similar parameter space from before, but it's enlarged. This is taken from the GitHub page from Kieran. He has a lot of these very nice plots that are up to date, because there's a lot of exclusion and experiments, monthly publishing results. So it keeps this up to date. But yeah, I just want to say that we're focusing on a very particular part of the parameter space where we want to solve the strong CP problem, so lie on this yellow line, and essentially be a dark matter at the same time. So we're looking really between micro electron volt to milli electron volt masses, which is, as you can see, where these axion heloscopes are trying to detect the axion. So what is a heloscope? A heloscope is an experiment that has been engineered to detect galactic axion, called axions, so axions that are dark matter. This was originally proposed by Sikivi, so that's why the standard procedure for finding axion is called the Sikivi cavity. This was proposed also a long time ago. But in a nutshell, this cavity is essentially an empty, you can imagine as an empty cylinder. It's typically made of copper. And you want to exploit the axion in interaction with photons. So axion interaction with two photons is called the Primakov effect. But you can supply one of the photons with a magnetic field. So you put the cavity in a magnetic field, and you hope to trigger this interaction between axion and photons and detect a photon in the cavity. Now, the keyword here is resonant, because this conversion of axion to photon only happens if you precisely match the wavelength of the axion, which is the inverse of the mass, or the inverse of the frequency, to the mode, one of the modes of the cavity. So roughly speaking, the size of the cavity. If you don't match those, then you're off resonance. You won't see anything essentially. But if you're lucky and you get the right value, then you should see a peak in your spectral density. So you should see more power in a certain part of your spectrum above a noise. So yeah, it's very crucial that you know what the frequency of the axion is, which is that's why we need a numerical simulation to tell us where the mass is. Otherwise, these experiments are not ideal to scan parameter space, because they hope to work on resonance. So this is the formula for the power that is deposited by an axion, and that can be this power can essentially excite a mode of the cavity and can be measured. I will go in just a second on what all these quantities are, but I want to first point out what are the numbers we're talking about. So the typical power that an axion heloscope should try to detect is 10 to the minus 22 watts, which is insanely small and definitely above ambient noise. So you need to cool the system to millikelvin temperatures. You need to make sure you have no noise added to your system, which is extremely challenging. So this gives you an idea on you just don't need to know what the resonant frequency is, but you also have a very small power to detect. The other thing I want to point out is what are we mostly focusing on when talking about our relation to heloscopes, is that what is the actual signal that you can extract from your Fourier transform. So this is a spectral frequency, the spectrum in frequencies, and again will depend on the coupling and the energy density and the mass. but it will have a typical spectral form, which is related to the velocity dispersion in dark matter. So this is where we will come in and how we can inform the haloscopes on what this typical line shape could look like. So yeah, so this is a collection of all the exclusions so far. So this is up to date to the exclusion in coupling versus mass. You can see that at order 1 microelectron-volt masses, the haloscope are able to reach the target lines. I think this is ADMX. But the challenge is to go at higher masses, as I will explain in a second. But as I was saying before, since we work on resonance, we don't know what the frequency is, and our haloscope have to be able to tune, so to scan in different frequencies. So the figure of merit for them is the scan rate. So how fast can you basically probe your parameter space in the axion mass as a function of time? Is it going to take you? How long is it going to take you to probe a certain parameter space? So the first dependence is set by nature. So whatever the axion coupling is, in this case, you would want to match this coupling to whatever your model tells you. So the KSVZ and DFSZ models. The local energy density is also playing a role. So how much dark matter do we have around us? It will tell us how much signal we have. So and how good our haloscopes are at work. And the rest are all up to the experimentalists, the rest of the parameters. So in green, I've highlighted those who are related to the signal. So what can you do to enhance the signal? Definitely a large magnetic field. You have a very steep dependence on the magnetic field, so that you want it as large as possible. The volume of the cavity is also something which is really important, and it could be a challenge, as I will explain in just a second. Then the quality factor is how good your resonator is at keeping to a coherent oscillation, and other factors which are related to the geometry of the cavity that can enhance or suppress the signal. And then everything else which is related to the receiver part. You want to not only maximize the signal but suppress the noise. So you would want to put the cavity to cryogenic temperatures, and you want to make sure you detect your signal, your photons, with as less other noise as possible. So let's put some numbers. If we want to target KSVZ and DFSZ with an optimistic cavity, you get that the scan rate is about 1 gigahertz per year for KSVZ and about 20 megahertz a year for DFSZ. Now, if you look at how big the parameter space can be, obviously this is in electron volt, not in gigahertz, or in hertz. But this means that at this rate, even with optimistic haloscopes, it will take hundreds of years to, even with multiple haloscopes targeting different parameter space, to cover all of this. So this is very challenging, and so that's why experimentalists will have to come up with new ways to exclude the parameter space faster, and we might be able to say something with our simulations if we can maybe improve the scan time just from a theory point of view. So the challenge is to maximize signal to noise. The second thing I want to say is that the volume scaling is actually a problem, because if you go at higher frequencies, you go to smaller and smaller cavities. Higher frequencies, you have a smaller wavelength, so you have to match the wavelength with a smaller and smaller cavity. So this is a picture that I've taken of the organ experiment that I've taken when I visited the University of Western Australia in Perth. And this is the size of the cavity, is very tiny. So plus the volume scaling is actually killing your scan rate. So all I'm trying to say is that if you want to go at higher masses, which is, as I will say in a few slides, where the simulation tells us to go, it's going to be a challenge if you use conventional haloscopes. With that being said, there are experiments that go beyond the standard picture, but I'm definitely not going into all of those details. So since I'm not an experimentalist, I will focus only on what we can get with whatever they have as a setup, and which is more related to the statistical analysis of their signal. So what are they actually excluding once they have a fixed signal to noise ratio, or fixed signal to noise? Because in particular, our signal would depend not only on the local energy density, but on the distribution in the frequencies, which is essentially related to the distribution in velocities. So if we know precisely what is the distribution of the dark matter around us on a very local scales, then we know how sensitive they actually would be to a discovery or an exclusion. Okay, so that was the first part. Now let's go into what we actually do with the simulations. So what is the role of the simulations? As I probably hinted already, there's two ways to go about this. Once we need to know where do we lie in this horizontal axis, and to answer this question, we need to know the overall abundance, because once we have the overall abundance computed precisely from misalignment and contribution from topological defects, then we can single out a value of the axion mass. And I'm telling you already, we don't have a final answer for this. So there's huge uncertainties from our simulations. So I will show you just in a few slides where the predictions from our simulation lie. But essentially, the first role of the simulation is to tell us where to look and where to build your haloscope. The second issue is on the distribution of axions, because what they actually quote here in their limit is assuming a particular distribution of axion to be to be a smooth background, and to have a local value of the energy density which is the same basically everywhere locally around us. So if that assumption is lifted, then what are they really sensitive to? So this is the second question that the simulation can tell us. Okay, so what are the simulations? I like to put them into a cosmological timeline, as you do in cosmology, and I like to think in terms of redshift, but if you like, this is the inverse of the scale factor. So really whatever is more intuitive. So you have a phase transition where you have the spontaneous symmetry breaking a very large redshift, but only at a redshift around 10 to the 13, where you have, because of the interaction, you have the axion starting to behave as dark matter, and you have this domain walls and string network collapsing, as I will show in a second. So what are you seeing at the moment here is energy projection. So you look at the energy in the field and you're projecting along one direction. So you have a way to have a three-dimensional effect, even if on a 2D plot. So you're literally seeing the strings that are surrounding these domain walls. So you can see the domain wall tension and the strings as yellow and green. And after this topological defect network has decayed, the number of densities is essentially conserved. So the prediction for the axion mass doesn't have to go further than that. But we want to go further than that to look at the actual distribution, because at some point later in the universe, the fluctuations that are left by the topological defects will collapse gravitationally and form what we call mini-cluster, mini-halos at very small masses and very small scales. So again, here you're seeing a similar projection from an embodied simulations that is essentially carried from the previous simulation. So the goal of the two stages in the cosmological timeline is again to find at the beginning the right mass, and the second one to find the distribution and therefore the local amplitude of the field. So let's look at the first part. So you'll see shortly a movie of one of these simulations. So just to provide any context, we are normalizing where tau equal to 1 is essentially the time where the mass is comparable to the Hubble scale. So when the oscillations start and the axion mass becomes relevant, and then these tau scales with like the scale factor in a way. So let me play this movie. And you have at the beginning a network of strings that emit semi-relativistic axions, but about a time equal to, you see that the domain walls are formed and also will drag the strings and collapse the entire network and leaving some overdensity on very small scales. But as you can see, initially the strings are in a scaling regime, but then they are abruptly collapsed by the domain walls. And as you can see at the end, you have a frozen field. You can see literally the wavefront freezing as the axion become more and more non-relativistic. Okay, so what are the strings? Yeah, well, they're a crucial part of all this simulation business because they give us they should give us in principle an answer, but we have a huge uncertainty on the modeling. But strings are essentially a solution to the Klein-Gordon equation. So you have the complex scalar field phi. So you have your Hubble drag term, your gradient, and your potential. This is the symmetry breaking potential that I was showing before. And if you want to look at this in an intuitive way, I already hinted at this before. you can see that the axion field will wrap the fundamental domain from minus pi to pi continuously. So if you look around this green circle, you see that the value of the field goes from white to light blue to dark blue to black to dark red, light red, and back to white. So essentially, it's doing a full circle. Now, this is just a 2D slice. You extend this in 3D, you have a string that essentially goes through the box. So in configuration space, you have a string-like filament that has a wrapping of 2 pi around it. But what's maybe more interesting to look at is in field space, because we know that the axion field lies as a circular direction on the Mexican head-like potential. And if you continuously shrink this circle at some point, you'll find yourself at the top of the potential. So the string core is essentially residual potential energy from the symmetric phase in a way. So the axion string core, which is related to the scale, so the size of the core is the inverse of 1 over, so it's 1 over FA, is essentially telling us that there is more potential energy in those regions. But still, there is an interaction with the rest of the axion field. So this string can emit, essentially, can couple to axion and emit axions in the process. So we want to compute how many of these axions are produced by these strings. Now, the string being a 1D filament, a 1D topological defect, will have a tension, so an energy per unit length. And why I'm pointing this out is just because there's a logarithmic dependence on the string tension, which will depend on whatever IR and UV regulators you have. The UV regulator is the string core itself, and in a string network, the IR regulator would be the inter-string separation. But what I want to point out here is that as the universe evolves, the Hubble scale will decrease, so the separation between these FA and H becomes larger and larger, which means that the string tension is acting as a proxy for time. So as time goes on, the string logarithmically increase the tension. And this is actually one of the issues, right? Because we have a multi-scale problem. We want to be able to resolve with our simulations the core of the strings with a few grids, with a few grid sites, but we also want to resolve the dynamical scale of Hubble. So we want to be able to, as the universe expands, simulate more and more. So we put some numbers in, and from when the string network forms when the Hubble scale is typically close to FA, and when it collapses, the log increases from order 1 to about 65. So this is very challenging because with simulations, we can only reach about log equal 10. That's essentially limited by the fact that you can get as big a grid as where your computer can fit in memory. This can be done with different methods. So I'm pointing out state-of-the-art simulations that have come just last year. With a uniform grid, you can reach log equal 9 or so with 11,000 Q points. We're talking about terabytes and terabytes of RAM. So you need a large supercomputer to do the simulation. Alternatively, you can use an adaptive mesh refinement approach where you put more points only around the strings and you save up your memory and you end up reaching a log equal 10. So this is the work from these people down here. Now, what is the actual quantity we want to? So what I want to say here is that from log equal 10 to 65, you're very far from the real answer, and you kind of need an extrapolation. And what you need to extrapolate is how many axions you have been producing from the strings, and this is done from the emission spectrum. Essentially, you look at what wavelengths your strings are producing their axions, and you have two different cases. And if the emission spectrum is IR dominated, you have that the abundance is enhanced by the strings. So the computation from so the relic abundance produced from strings is much larger than the standard misalignment value. While if your spectrum is UV dominated, so if Q is more than 1, this spectral index, then your contribution from strings is not going to be too far from whatever the misalignment is telling you. So, and what I want to point out is that within our simulations and the simulation in the literature, there's no clear indication whether this Q is larger or smaller than 1. So at the moment, we don't know if strings are pushing the relic abundance to a much larger value or if they're not. So there's a large uncertainty on this. So there's a lot of things that I didn't say, but essentially just let me bring a point here. Both with the uniform grid and with the mesh refinement grid, you still have a large parameter space so to be covered. So the prediction for the uniform grid is that the mass should be anywhere between 100 and 500 microelectron volts. The AMR prediction is sort of more narrow when considering only the strings, but then when looking at the production of axion from the walls as well, from the domain walls, you can get to a value up to 300 microelectron volts. So let's put it in the plot. I'm also adding another simulation that was done in 2020 by the Gorgettos group. As you can see, that there is no clear prediction because, first of all, there's not a convergence in the literature here. So we can see that the prediction from strings here is entirely exclusive from whatever prediction you have here and here as well. But more importantly, all these predictions are very far away from where Halo scores have been looking so far. So there's literally nothing here that have been excluded. So it's basically saying our best guess for the parameter space is yet unexplored, and maybe in the future could be. But as I was saying before, it's very challenging at those values. Okay, the second part of the timeline is to map our previous simulations, which was a lattice simulations, and mapping into n-body particles, and then let it run just by gravity. And you can see that at the beginning of the simulation that takes place at a redshift of 10 to the 6, so way before matter radiation equality, field looks like it has residual fluctuations that are being left by the topological defects, but they will start gradually collapse just by gravity. And you can see that at matter radiation equality about 3400, you already have clamped regions that are formed. And as time goes on, up to final redshift time, this early collapsed mini cluster will merge hierarchically into larger and larger halos. So just a word of caution here, because I get this question a lot. This is not standard large scale structure. We're basically here in the spectrum here, our dimensionless power spectrum. We have a linear power spectrum here. We have our measurements from CMB and galactic surveys, and we're way over here. So we're talking about subgalactic scales. So when you look at the plots from before, we're talking about sub-parsec scales, which are well subgalactic. So what are these mini clusters? Well, they are essentially bound objects. So we can simulate them with n-body tools, which is great. The first time that this has been done with quite a large resolution was done by Egemeyer's group in 2019. So the box size here is about a parsec. So the mini clusters are, I would say, milliparsec or so. And what they found in the paper is that most of the axions will end up bound in those objects, as you would expect, about 80%. And the other thing they point out is that they seem to have an NFW profile, so this Navarro-Frank profile, which is a universal profile for dark matter, which is sort of well known. And this has, knowing the profile of these mini classes, is really important, because we need to understand how dense and how compact these objects are in case they might undergo tidal stripping because of interaction with the galaxy. So the point here is that I want to say is that there typically is not enough resolution to tell the concentration of these objects. So here I'm highlighting a result, a very recent result as well, where the n-body simulation had more particles than the initial simulation. So in this case, it's 2048 cube particles. And what it seems so far is with the new results is that there is a slight preference for a profile which deviates from NFW. But so this modified NFW has a R to the -2 dependence at the core instead of R to the -1. So it looks like the mini classes actually might be denser than what was previously thought, which could have implications, as I will say in just a second. So in here, basically, just saying the quality of the fit between the NFW and this modified profile, showing that for larger and larger masses, you have a slight preference for this modified profile. But the idea is that this is still at a very high redshift. This is a redshift of 1500, so very early in the universe still. And ideally, we would want more resolution to tell essentially how this mini cluster should behave in the later part of this evolution. The other thing we looked at is, well, instead of focusing too much on the mini clusters, well, if you think about direct detection, we might be on one of these empty regions. So now you're looking at an actual volume rendering of and body simulation. And you can tell that most of it is essentially voids, what we call mini voids, because they are about parsec size. So we ask ourselves the question, well, if we are in one of these voids, and just statistically speaking, there's a better chance that we're in there rather than in one of the mini clusters. What is the actual density that an experiment should be probing? Because even though these voids are relatively small, a parsec is large compared to the speed of a solar system as we move around the center of the galaxy. So if we are in one of these voids, we're not going to be leaving them anytime soon. So we calculated this. So we looked at the mini void typical energy density as a function of time, and it looks like it stabilizes to a constant value about close to 10% of the large scale average value. So this was sort of like at the bottom of how bad does it get if you're in one of those voids, how much energy density is in one of these regions. And I will comment just towards the end on the implication for the experiments. But as you might have noticed from my timeline, the story didn't end as 10 to the 2. The redshift of 10 to the 2 is when the universe was 10 million years old or so. So there's a lot that happened after. The galaxy starts to form right after. And you might imagine that this clumpy distribution at small scales will start to interact with the forming Milky Way potential. So all these mini clusters will have to be able to withstand tidal forces, not only from the potential from the Milky Way itself, but interaction with newly forming stars. So in here, you see a very nice picture here of a typical mini cluster interacting with the star, and you have an impact parameter. So you want to know if the stars have enough energy to disrupt the mini clusters or leave them impact. So this is another work that we've been doing. This is a simulation of the orbits. This is a Monte Carlo simulation that we used using a code called GalPy, essentially looking at the orbits of this mini cluster around the center of the galaxy. And here you see this particular orbit that is plotted in here, and as a reference, you have a solar position. But the idea is that as the mini cluster goes around, in the Milky Way halo, every time it crosses the stellar disk, the stellar density, which is plotted here as a function of time, will peak every time the orbit will cross the disk. And every time you cross the disk, you have interaction with stars, possibly many at one point. And the stars will impart energy, which is typically related to the impact parameter, relative velocity, and other parameters, and so on. So you want to study what is the mass that is being stripped in each of these encounters. And as you can see, we separate the isolated and merged mini cluster in a way that the merged ones are, formed with a hierarchical merging, and I have larger mass, and they seem to be prone to lose more and more mass every time they encounter a star. So this type of simulation was first done a few years ago by the group of Kavanagh, and what they looked at is the survival probability of this object. So how many of them survive, or versus how many of them lose all their masses because of this tidal stripping. And they find that if you have an NFW profile or a power law profile, the picture changes quite a lot. So if you look at this line here is location, the solar neighborhood location, and they say that there's a 50% chance that you disrupt a mini cluster if the profile is NFW, while they should be surviving it a power law. So the increase in the resolution of simulation can tell us more precisely what the profile of these objects are, or their concentration in a way, and how resilient they are to this type of interaction. We did a similar Monte Carlo simulation, but we asked a different question. Instead of looking at the survival probability, since we want to focus on direct detection, we want to know how much of their mass is spilled in the outside, how much of this mass fills back our mini voids. So we model the stream as essentially every time it has an encounter, it drops some of the mass, so a shell of mass gets lost and starts to gradually form a tidal stream. We took a very simplistic modeling of these streams, just to give a rough estimate. And so you might imagine that because of the mini cluster are likely to lose a lot of their mass, especially the very large ones that are not very, very dense, you might expect them to form a lot of tidal streams. And here you can see that as we move along the center of the galaxy, you might encounter more and more streams coming from all different directions with all different thickness and all different velocity dispersions, which are related to the velocity dispersion of the initial mini cluster. So the result from our Monte Carlo simulation is that we expect about 1,000 of these things all around us at any point in space. And their energy density, the sum of all their energy adds up to about 85% of the locally measured value. So the locally measured value takes place is inferred on scales much larger than what we can actually probe as we move around the center of the galaxy. So in a way, you're very close to the estimate. I think with the modeling, we might be underestimating a little bit this value, but in a way, it's sort of like a consistency check to make sure that we're always kind of probing the local value of the dark matter that is inferred from our observations. So in principle here, you look at one of these realization of these 1,000 streams, and you can see that they all have different velocity dispersions. So you can imagine the velocity dispersion in kilometers per second. And also, as we move through through many of these streams, they would stay in our experiment if we are at the right frequency for a different amount of time. So most of these streams will stay about 100 days to a year because they're quite large. And as I said, as our solar system moves, we're still probing most of them within this time frame. So just to give an idea of how complicated the system is, because this is also generated from a simulation. It's not we don't have an analytical expression of what the distribution looks like, so it's very complicated. Yeah, so let me move on to the final part of this talk, which is what are the simulation telling us when it comes to experiments. Already hinted how to go in the parameter space, whether it's horizontally or vertically. So for this, since I don't want to focus too much on the prediction of the axion mass, but more on the distribution of the axion around us, I want to focus again on this signal. So the spectral density of axions should be proportional to, again, coupling squared and mass. And we have the local value of the energy density and the distribution in speeds that is in the axion. So I touched upon both of these two issues because for the local value of energy density, we estimated that if we are in one of these voids, you would have an energy suppression, so your signal will be suppressed and your constraint goes bad. Because every coupling that you're actually constraining is for a certain value of rho. And if your assumed value is that you have, the inferred value, but instead you would have 10% of that, then your exclusion would change. And the second issue is on if the line shape, so if the distribution is not smooth, I will touch upon this in just a few slides. Then if you have enough resolution to resolve all of these streams, then your signal changes and your analysis changes as well. So let's focus on the first issue. So as I said, our current exclusions are for a fixed value of rho A, and rho A is usually assumed to be whatever is inferred at large scales. But if we are in one of these voids, and if the mini classes are dense enough not to spill too much mass in these voids, then what you're actually probing is 10% of the value which is inferred. So you would want to move, since you have G square rho, any exclusion in G goes with the square root of rho. So square root of 10% is a factor 10 is about a factor of 3. So you would move all your constraint actually by a factor 3. So an experiment here that would exclude DFZ, now it's really not excluding DFZ anymore if we are in one of these voids, but it's actually excluding barely KSVZ. So yeah, this is in a way bad news for the experiments because they have less energy to extract a signal. So the nominal constraint is actually shifted upwards. The second issue is something that we're looking at the moment, so I'm not going to go into details so much, but the idea is that you can have the opposite effect. You might be lucky to find the axion even if you're not, you might be lucky to have a better benchmark rather than the nominal benchmark because you're not assuming that the distribution is smooth. And so the way it works is, well, as I was explaining before, the oscillation that you would detect is very coherent, and it would be peaking at the value of the mass. But at some point, if you wait for long enough, the frequencies will start to shift because an axion with a slightly different velocity dispersion will appear in a slightly different part of your spectrum. So your spectral your spectral signal in the spectrum will start to develop whatever you have, whatever the distribution in the velocities you have. So the typical velocity dispersion is 10 to the minus 3 in natural units, which means that up in 10 to the 6 oscillation, you should be coherent. But if you integrate for times longer than this coherence time, then you should start to see the dependence on the velocity appearing. And the coherence time, I want to also point out, it's a very small time for a typical axial mass. So usually experiments within a second are already in a regime where they can already start to see the deviation from this monochromatic signal to whatever the line shape looks like. So as you integrate this T int is the integration time, or the time that you take to take the Fourier transform. The larger this time, the better your time resolution will be because it will be inversely proportional to that. And if you have just enough resolution to go around this coherence time, so now this integration time is very close to the coherence time. You just have a few spectral beams here, and the signal is not very well resolved. You have a peak. And now I'm just normalizing the horizontal axis to make it more understandable. But essentially, the idea is here, whether you have a background or you have a signal which is made of void plus streams, they will look very similar because the resolution is really bad. As you increase the resolution by a factor of 3, by 3 orders of magnitude, you can already tell that you would gain a lot by having this very good resolution, because now if you resolve, if you have enough frequency resolution to resolve the velocity dispersion on these streams, they will start to appear as peaks in your spectrum. And again, the height of the peaks will depend on at this point on your frequency resolution. So you want to have a frequency resolution which is good enough to show up, and you would have definitely a difference between your smooth background, which is this Maxwellian line, versus a clumpy background made of streams. So this was the idea that we had just a few years ago, and we looked at the spectral shapes. So this is generated again with the Monte Carlo simulations. But the idea is here that if you have a large enough resolution, first of all, you can distinguish between a smooth, which is a pre-inflationary scenario, to a clumpy post-inflationary line shape. But also, you would have an enhanced signal-to-noise ratio, which is what the experiments would want. The problem with this, and I'm not going into the details since I'm about to wrap this up, is that now our signal is kind of non-trivial to describe. So coming up with a statistical framework where we are confident that our 90% exclusion is sort of robust becomes a bit more challenging, because now we have a lot of streams. We don't know how many precisely. We know the distribution of the widths, but yeah, this is very done in a very random way. So we have in other words, we have a lot of parameters to model. And the other issue is that the signal might not be persistent, because as we move around the center of the galaxy, we might be crossing through some streams. And as we move, you can see that some of the peaks will look at, would be at later parts, at different parts of the spectrum, if you take a measurement at a later time. So I'm spacing here within 4 weeks. You can see that some of the lines have shifted in frequencies because of velocity shift, because of the Doppler shift, essentially. And some of them could disappear because you cross the stream. Some of them appear in places you didn't have before. So this is extremely complicated because now you have all these streams that are essentially time variables. So yeah, I'm not going into the details with something that we're figuring out at the moment, but the idea is that because if you have enough frequency resolution, you would have a larger signal to noise ratio, so you would actually be more sensitive than what you would think if you assume a smooth background. So you would go by as much as a factor of 3. This is our early estimates downwards. So this is better news for the experiments. And this is something that they can use in order to maybe revisit their constraints or maybe plan future telescopes around. Yeah, so I'm wrapping this up. I just want to acknowledge that all of these simulations have been taking place. Most of the simulations have been taking place at a supercomputer in Canberra from NCI. So this is some of the pictures that I've taken when I visited the center. So you have all the compute nodes here. They also opened one of them to show us the CPUs and all that. I thought it was fascinating. Yeah, let me leave you with the conclusion, which is if you assume the current understanding that the local densities, whatever is inferred, and you have a smooth background, you have these constraints that are cited in the papers, but this can change if you vary the assumption on both the local energy density and so the distribution, the spatial distribution, and the distribution in velocities, whether upwards or downwards. And it might be that the real thing could be a combination of these two competing effects. But yeah, this will need to be done in future works. So I'll leave you with the summary, and happy to take any questions.
Thank you. We have questions here.
So maybe I can ask one. So if you have those velocity dispersion in there, and your peaks show up randomly, more or less,
yeah,
how certain that you saw a signal?
Well, the idea is to look at how many peaks you would expect above a certain threshold, right? In a smooth background, you know very well what the spectral shape looks like, and it's kind of smooth, so you wouldn't expect a signal much larger than this kind of background. But if you count how many peaks you have above a certain threshold, you should tell the experimentalists you should see at least this many peaks. If you have this resolution, it's all a matter of resolution. Once you have fixed a resolution, how many of the streams are actually resolved, and what is their typical peaks, because they pack a lot of energy within those very narrow frequency beams. So I think the answer would be to literally count the peaks above a certain threshold, so they can sort of exclude the possibility of this scenario or not.
Okay, so and how much noise do they have in the environment typically in those?
Well, yeah, the noise is pretty bad. So typically the cavity are cooled to millicavity temperatures. But the problem is not really on the temperature so the way they model the noise is to an effective temperature of the system, and that is a combination of whatever you have in the cavity. So the walls of the cavity, what's the thermal noise that you have. But then you have a noise that is typically added in the amplification stage. So in that case, it becomes really bad at high frequencies, because in that case, even if you are at a quantum at the standard quantum limit, you have a quite large noise, because your temperature noise will be basically the frequency of the value, or the frequency of the field. So that the challenge is mostly on the receiving end. That's why now they're trying to develop photon counters, where they're trying to go beyond this standard quantum limit that is typically given by the linear amplifiers. Yeah, and basically the rest is engineering a cavity and a refrigerator that is at millikelvin temperatures. Yeah, I think that's most of the challenges.
Yeah, thanks.
Anyone else here would like to ask anything? You're right.
Yeah. Like, I wanted to ask, like, do current experiments have this, like, will they be able to resolve? So they have enough resolution to resolve the streams?
Yeah, that's a good question. They do, in fact, ADMX, so one of the leading experiments, so they currently target this parameter space. So they're a bit far away from the post-inflationary case, because if you recall, the prediction from the simulation is you're around 100 microelectron volt. So they're far away, but they do have enough time resolution to resolve the streams. And that essentially because they have a large enough integration time, such that the inverse of this integration time is smaller than almost all the widths of our streams. So we don't expect our streams to have a much narrower velocity dispersion than that. So they are able to resolve pretty much all of them. Now, for this new experiments, they will have to do their calculations as well, because in that case, the coherence time changes for them. So the integration time will change as well, since they look at the higher masses. But essentially, if you wait long enough, you can resolve all of them. So it's just a matter of finding the optimal value of integration time. If you integrate for too long, then it takes too long to exclude a certain frequency. Your scan rate is bad. So it's always finding the right spot, the sweet spot.
So in the end, it only depends if you integrate enough time, like if you measure enough time, right? Like
yeah. If you look in here, as you could wait arbitrarily long enough, and you would resolve all of them. But at the cost of spending a lot of time at a scanning frequency. So you would want to make sure that you scan large enough but short enough, so that you're fast and you move on to the next frequency.
Yeah, thank you very much.
Anyone else here would like to ask something? Anyone online would like to ask a question? Please just speak up.
I had one. Yeah, sorry, I had one. So how sensitive is the simulation to the shape of the axion potential? Does it matter that much? Like if I had a crazy potential with polynomials and which would take minima, but so in the Klein-Gordon equation, that would show up as whether something dominates over.
Yeah, good point. I didn't discuss too much this issue. Usually that dependence comes on how steep your temperature dependence is in the mass. Usually you go from a zero mass to the zero temperature value, but how steep you get there. And that is essentially the uncertainty is what they call here NQCD. So you typically parameterize the mass growth as a power law. And if you use a dilute instant gas approximation, you get n equal 8. If you use lattice simulation of lattice QCD, in this case, you get n equals 7. So you have a bit of an uncertainty on this. However, I don't think it's really the largest uncertainty in narrowing down the mass. That is mostly on the spectral index. So how efficient are the strings in radiating axions? But yeah, this is uncertainty is included in some of the simulations.
And so it does not, in the end, down the line, impact how many miniclusters you form, or what because does that affect down the line when you do the minicluster simulation?
No, not at all, because the number density is conserved way before they form.
Oh, the number density is conserved. I see.
Yeah.
Okay, that's right. Okay, yep. Cool. Thanks.
Any more questions? Anyone online? Just speak up. I'll just ask one. You talked briefly about the concentrate, the halo profile, and how that changes the way tidal stripping happens. Can you just elaborate a little bit more on that? And also, when with your simulations of the tidal stripping, how strongly would the different profiles affect your signal in the end?
Well, we find a similar results that is in here. So the way they the way they did their analysis is to divide power law sort of population of miniclusters, which are those who form right at matter radiation equality and kind of don't merge hierarchically. So they stay kind of isolated and they have a more power law looking like profile. Well, the NFW is to essentially model those miniclusters that merge at later times. In reality, I think it's what really matters is the structural parameter of the profile. So a way that we are trying to maybe look now at the analysis is to look at the numerical profiles and look at the actual concentration rather than categorizing them as an NFW or power law. And so try to look at those structural parameters and then compare them with the previous Monte Carlo simulations, because those structural parameters actually enter the pipeline in this Monte Carlo simulation. Every time you have this delta E is sort of related to how dense the object is. So in a way, if you distinguish them between NFW and power law, you can tell, and we had very similar results, that NFW is very prone to lose a lot of mass and almost destroy the entire mini cluster. But that being said, the simulation that we have so far are very limited in resolution. So the simulation that we have been running for the mini voids and all these things, they don't have enough resolution to resolve the core, the scale radius for NFW.
So you can't resolve the profile, which I understand.
Yeah.
But I guess what I'm asking is, with your predictions for the halo scope, did you vary the concentration? I mean, even if you just treat the concentration parameter as a free parameter, was it just for one value of the concentration, or did you look at?
We're allowed to vary that, and it looks like so. I think I have a slide for this. So we look with at different parameterization of the pipeline, and essentially it looks like the peak of the distribution. So the sum of the stream densities is very, very similar, but the spread looks a bit different. That's also related to how you model the streams, but I think that the way you model the concentration doesn't really enter too much in the final answer. But in terms of all the velocity dispersion, that could have an impact. And we didn't look that into detail. So far we just provided a sort of framework of what to expect, but it will need to be refined with more information on the actual concentration of the halos.
Yeah. Okay. Thank you. Anyone else would like to ask anything? Yes, one more. Yeah.
Like I wanted to ask about the strings. So can you exclude regions of the parameter space if you have long-lived enough strings? Because I thought like they can be a problem for cosmology, right? In some sense, if you have many topological defects.
Yeah. So in this case, as you can see at the end of the simulation, they disappear. That's because the domain will destroy them. But yeah, we kind of put ourselves in the scenario where this happens, and that is the domain wall number is equal to 1. In that case, you don't have many degenerate vacua, so the string will actually be destroyed together with the walls. So you wouldn't have strings around today. But if your domain wall number is larger than 1, as it happens in some of the UV complete models, then you need to introduce a bias in order to destroy the string wall network. Otherwise, you have this domain wall problem, right? That they would end up dominating the energy density today. So we're sort of like picking the vanilla scenario, n equal 1, everything collapses, so they're not around. But that's not the full story. So yeah, thanks for pointing that out.
Yeah, because one of these benchmark models has a different one, right? I don't know if it's
the DFSZ doesn't have n equal 1. I mean, you can get crazy with theory and come up with a way to have n equal 1. I'm sure you can do that. But the vanilla scenario is that KSVZ has n equal 1. So we're basically targeting that. Essentially neglecting the possibility of having n equal 2 or larger. There are simulations of larger domain 1 numbers that are very complicated, and if you want the network to collapse again, you need to introduce a bias. That's the only way.
Cool. So, any more questions anywhere? Speak now or wherever, hold your peace. Okay, they're holding their peace. So then we'll conclude the formal part of the